Okay, so I'm sure many of you heard of property-based testing at some point or another, and usually something sounds very promising. Usually, it goes something like this: you write one property for your code, and then you that should hold for any input of your code, and then you get hundreds of tests for free by just generating random inputs and verifying that the property holds the way you want it to hold. What is this noise? Sorry. And so it's much better than writing some measly tiny unit tests. You get lots of tests at once. And it sounds all very promising, but then they show you some examples. So for example, you can check the sensitivity of addition. It's nice. And you can validate your own reverse function that you reverse it twice and it's still kind of like the right thing should be. And then you're kind of left on your own to figure out your own properties for your own code. And I really like the idea of property-based testing. I really want to apply it to something, but I find it very hard, and despite my best wishes, to actually approach it with my own code, approach property-based testing with my own code and kind of define something on my own, because the number of times I'll write reverse during my career is probably limited, and I won't be doing new integers probably anytime soon. And there are, of course, talks tackling these issues and trying to kind of give you ideas and hints of how to get your own properties, but I'll try to tackle it from another point of view. So we're going to look at a case study of a tricky kind of production bug, which was where we used property-based testing as sort of a debug tool to help us resolve the bug. And with there are a few pillars of property-based testing, and that's defining properties, which we'll use here to define simple properties for a system that will hold there for every input. We'll use random data to actually debug and reproduce the bug just like we do it in production, and then we'll use another nice property of property-based testing, and that's shrinking so that we can minimize the bug in a way that's comprehensible and makes it easier to understand what's actually going on. So before we can actually begin, we'll need some background about the system we're going to debug. So because I didn't have any nice quotes, I used GPT to generate quotes for me. So I don't know. Okay, so I'll start off by saying that this is inspired by a real production issue that occurred in the system I was working on, and I really did use property-based testing to debug it, but the examples I'm going to show you are so obfuscated that even the people who are working on this code to this very day are probably not likely to recognize this bug as I'm about to show it. So with this disclaimer out of the way, so let's imagine that you're trying to make a startup. And you want to maximize buzzwords, because that's the way probably to succeed on a startup. So the more buzzwords you have on your landing page, the more likely you'll be successful. And so blockchain and deep learning and stuff like this are just words that we really want to use on our landing page. So with this in mind, we can build a startup. So we have to start with some deep insight about something so that we have a startup to start on. So people really don't like ads. And with people having much more sophisticated and powerful phones, there's lots of compute being wasted on idling phones that are just doing nothing useful for anyone. And so the idea is that we can sell off mobile compute from users to the highest bidder. Seems like a plausible thing to do. And by using diverse kind of jobs that we submit on our mobile compute little kind of edge cloud, we can maximize the buzzwords that we can kind of legitimately use on our landing page. And of course, our users in return are getting no ads service, so that's a win-win for everyone. So here's the review of a high-level overview of the system we're going to be looking at. Of course, we can't present anything to anyone without some kind of buzzwords, so here they are. So we have a bunch of job providers that are going to provide jobs for us, so that they're requesting for us to execute stuff. So they're sending us requests with various jobs, and we have at this moment supporting 3 kinds of jobs. So we can mine Bitcoin, or we can do train some deep learning networks, and because we want to give back to the world, we're doing protein folding as well. That's little DNA here being folded in some way. So since we're actually running arbitrary code on client devices here, we're taking security very seriously. So before we're sending anything off to the users, we're taking it through a security manager, which rejects unsafe jobs and stuff, and then sends it to a job queue, which then eventually sends it away into client devices. And that might be called edge computing, so that's a buzzword. So the focus of this talk is going to be on the security manager. So this is kind of a zoomed-in version of the security manager. So this is probably the oldest part of code here, so it has lots of kind of weirdness and weird integrations, and the weirdest thing is the kind of batching that we're doing here. So for various performance reasons and legacy reasons, we're batching inputs by provider, so each provider can give us a batch of inputs, and we are creating a batch of batches before we send it to the security ranker, so that lets us kind of save time or whatever. Next, we're ranking the various jobs by their security ranking, so that we know which jobs are actually safe. But the ones that are kind of shady, you have a more advanced security tracer that does the kind of a deep insight thing on the job and decides whether it's sufficiently safe to send to the user. And because it's kind of dangerous for the servers that's running it, we have a security sandbox that can limit whatever damage to the server. And this is kind of the most fiddly part of our system because it's an expensive resource that requires careful management. And of course, we can't do anything without buzzwords, so we're using data science for the ranking. We're not just ranking or predicting stuff. And we have AI to do the tracing because so now we are familiar with the system to some extent. We're ready to dive into the production bug. So one day you get the bug report, and it looks like this. We're getting, after updating from Java 6 to 7, it's about time, probably way past time. We started getting occasional exceptions called security sandbox corrupt exception. And that's it, no other clues. That's the bug report, that's all we get. So we scratch our head and try to think about this. And the first line of defense always for experienced programmers is printline debugging. So we start with that. And so we look at the code that's responsible for the error. So this is the signature. We have this batch of batches that we're getting into our security manager, and we're doing some side effects. So we start by printing out some outputs and see what corrupts our sandbox. So this is an example input to our ranker that corrupted the sandbox. So now that we have this lovely input, which is quite small, we can try to create a unit test and see whether we reproduce the bug. So we have a small unit test that, given that input from before, we send it to our security manager, and we're checking that the sandbox is not corrupt after executing it. And we run it, and it fails. So no such luck in reproducing the bug. And although the input was corrupting production, it doesn't reproduce in a test. So if you think about it some more, it's quite likely that we have some kind of a stateful bug. So the sandbox is a stateful kind of thing, and so maybe it's a sequence of actions that brings the system into a corrupt state. And so at this point, we can really pray that it's not a multi-threading bug, because if it's a multi-threading bug, it's probably not for this talk anyway. But luckily, the security manager is very old and very sequential, so it's not likely to be multi-threaded anyways. And we can hope that the bug is sequential, and so we can try to reproduce it with a bunch of steps. So we take a longer trace from production, so this is kind of a long trace. It's quite long, but at the end, this is supposed to be failing our sandbox. And so we can rewrite our test with the longer sequence. In this case, we see we have a list of lists of job batches, so we have lots of nestiness. And the idea is that we're kind of making a few steps from our production output and sending it to the security sandbox, security ranker, and hoping that it actually corrupts the bug. And we run it again, corrupts the sandbox. And we run it again, and nope, nothing. So if the problem is stateful, so who knows how long the sequence that we're supposed to be running should be. So it might be days before the first step and the last step that actually corrupted our sandbox. And we can continue randomly picking out outputs from production, but it's tedious. And that's the nature of stateful issues. The cause and effect can be very far apart, kind of a spooky action at a distance. But why should we actually randomly pick out our logs? Why not just generate them randomly and see whether we can reproduce it that way? Okay, so now that printline debugging and unit testing failed us, obviously, we already tackled this problem with property-based testing, and the actual reason for this talk. So we're finally getting to that. So seeing how property-based testing is supposed to be very magical, it should be kind of a no-brainer to nail down this little bug. So we can start by defining our own very own first property. So it's very, very similar to the original unit test, but so we still have the list of job batches, but instead of a regular unit test, we're doing it for all. So for every possible list of batches, our sandbox should never be corrupted. So that's the property. It's a very desirable property for the system. We don't want any kind of corruption. And so, like in the last unit test, we're doing a list of batches, and so it should have the capability of getting us into the problematic state. And so, if you run it, we finally get green, but it's not the right kind of green that we actually got. So, what we just proved is that this property holds for our system, but we know that there is a bug. This property shouldn't be holding, and this should be red in some way. So this is actually a failure. So the property didn't manage to reveal the bug, so it's not as magical as we hoped it to be. But there's one thing to note here, the test was running very quickly, so it's probably not doing many inputs to our system. So we don't have much sampling. So if the bug is sufficiently complicated, we probably want something more, a deeper probe into the bug and have more outputs produced randomly generated for a test. So we can tweak the settings. Usually property-based testing comes with kind of low defaults where you run just like 100 samples or 10 samples or whatever. So we ramp it up to 2,000 samples, and we can run it again. And on the bright side, it is running, it's longer test now, it's 2.5 minutes. That's the bright side. The bad part is it's still green, and we want it to fail. We want the property to reveal, flush out the bug, and show how it doesn't hold for a system. Okay, so at this point we might just give up and decide that property-based testing is not for us, but this is not that kind of talk, and although I don't have much time, hopefully I'll have time to reach a more optimistic conclusion. So let's start to think about some more. So this is our security manager, and it has a few dependencies that it uses to do its job. And it's quite likely that our bug is kind of some weird interaction between the different components. And so the more interactions that we have, the more components we have, the larger is the state space of possible situations that we, possible inputs, outputs, and bugs that we can get. So it's quite likely that the state space here is just too large for us to randomly hit it inside the real system. So we need some way to reduce the state space into something smaller that we can probe more efficiently and have more likelihood of hitting the bug in a random walk. So what we can do is try to mock out part of the system and hope to kind of, on one side, to reduce the state space, but still keep the bug intact. So we basically want to create a partial model of the system that will still be sufficiently complicated for the bug, but not that complicated that we can't actually catch it with random inputs. But we need to we have to decide which components we want to actually mock. So this is where it's becoming kind of more speculative. We have to guess which components are relevant and which are not. It takes some practice and educated guesses, but we can just go from the last one. So the job queue comes after the sandbox, so it's kind of irrelevant. The security tracer uses the sandbox, but it's an external component. It's way too complicated to model it in a simple fashion. So we just put it aside and hoping that that's not the problem. And then there's this sandbox optimizer. So the sandbox optimizer is actually doing something pretty complicated. It tries to reduce the usage of the sandbox, figure out how we can open and close it fewer times, so it's not as disruptive to our computations. But unfortunately, it's essentially a pure function, a quite complicated pure function, and we could mock it out quite easily, but it's likely that either the mock will be too trivial to reveal the bug, or going to have it's too complicated and have its own bugs, and we don't want to reveal bugs in a model that is not actually relevant. So we skip for the optimizer for now. And the last one is security ranker, which is the last candidate left, and it's actually quite a good candidate for mocking because it's kind of a black box for us. So it does some side effect and gives us ranking, but we don't know how it works. So we'll choose to mock this out. And so we'll be guiding ourselves, we'll be following the types to deduce what kind of mock we want to create or what kind of model for the system we're trying to get here. So we can see that the output has, the output here has some nested structure. So ranked batch is something that is an option of list of something. It's always suspicious when you have types like that hanging around. But for us, it's kind of a map of what we can do. So there are three main scenarios that can happen. So the whole thing is running a side effect, but it's an unexceptional I/O, so it's probably not throwing exceptions. So we can ignore possible exceptions. It can return an option which can be empty, and it can return a list which can also be empty, but also or it can have lots of ranked jobs in them. So we have three major behaviors in our system, so an empty option, an empty list, and for the last one where we actually have to return something, we'll choose to just assign random rankings and hope that that's enough. So this is the model for our mock. This is the behaviors we're going to support, and hopefully it's small enough that we can actually reproduce the bug with it, but it's rich enough to still contain the bug, and it's not too trivial for our purposes. So this is the new rewritten test. So it's very similar to the old one, but instead of just having job badges, we now have behaviors as well. So each job badge is assigned as some behavior, and that behavior will define how the security ranker is going to respond. And we can run it now again, and it's failed again for the third time. It's really like my cue to give up, I guess. So the bug wasn't revealed by this property, and we really tried. And it seems that property-based testing is just not all that great. Well, the last slide is going to have the word questions, so if you see a dark slide, doesn't mean I'm just finished pessimistically and we're done. So, okay, it's time to kind of step back and see what we have here. So property-based testing is actually quite a rich topic with lots of history and lots of concepts and ideas. And there are lots of nuances, things that we should think about maybe before just diving into property-based testing. So we are hoping to kind of magically run our property and get everything working, but we have a fairly complicated bug with lots of interactions. And so maybe we should invest a bit more time into the actual process. So successful property-based testing hinges on generating good data. And what good means is very context-dependent, but for the purposes of this talk, we need to strike a certain balance with data generation. So the data should be random enough so we don't miss the bug, but it shouldn't be too random, because otherwise the state space becomes too large and we might just miss the bug because we have no chance of hitting it randomly in a huge state space. But in the specific use case where we have a known bug, we know that we're trying to catch something existing, realistic data from production, something that looks more similar to the production data, might actually help us to minimize the state space, minimize the randomness of the test, but still be relevant for catching the bug. So to see whether we have a chance of hitting the bug, it's a good idea to inspect your generators. So generators are doing some non-trivial logic for us. Let's take a look that they're actually doing what we require them to do. So here's the distribution of behaviors we get from our property-based test. So the distribution looks quite reasonable. So a third for each of the behaviors. So no reason to think that's not something we want. The jobs are also distributed evenly. And again, we don't have any reason to think that we should skew the distribution one way or another. But then we look at the providers. And the providers are kind of a mess. We're just randomly generating strings, and we have lots of different strings. And it's very, very unrealistic. So in the real production system, we don't have that many providers. We probably have like a few, like 10, 3, 4, whatever. And they're fixed. They're not changing in time. So this is a great way to reduce the state space, because by not producing so many random inputs, maybe we'll manage to kind of get the likelihood of hitting the bug higher. And we can fix this by making the generator more compact, so just 3 providers with the appropriate distribution. And that's much more realistic because, again, the real system is not that random. And now that the distribution is more reasonable, we can get back to actually running our property. So let's run it again. And it actually fails, finally, after like 4 steps. So our property caught something, so we have a real red test here. Not only did it caught something, it used shrinking to make this case very, very minimal. So we have only 3 batches with no jobs in them, and only 2 different behaviors that we are using, so only empty list and empty option. And with such a minimal reproduction of the minimal reproduction of this bug, we can actually trace it through our code in a way that's manageable. So here's a small print line debugging session again. So this is what the logs look like now. And to figure out what's wrong with this log, we can compare it to a presumably successful log. So in a successful log, we can see something here that for every batch that we're running, every sublist that we're running, at some point we're opening the sandbox for a provider, but then at some later point we actually close it. And this is something that the optimizer is doing for us. Instead of opening and closing them one after another, it lets us spread the load and open and close it more rarely, because that's opening for the sandbox for the provider is a heavy operation. What we see in our buggy trace that we're opening the sandbox for P3, but then we never close it and try to open it again. And that's our corruption here. So the rules of the sandbox API is that we cannot open the same provider twice without closing it in between. So somehow we managed to open it twice without closing it at all. And this actually explains why our bugs are, why the bug is so non-local. So it might take time before forgetting to close the provider until the next time we actually get it in production. So it might be days between the beginning of the bug and the end of the bug. And but the question is, why didn't we close the sandbox in the first place? So at this point, I don't have any choice but actually show you some code. I usually avoid showing big chunks of code, especially if it's terrible code, that's what it's going to be right now. But that's really part of the point. Bugs tend to be hidden in terrible pieces of code, and they're much more prone to bugs. So this is what happened here. So this is the code. And it is terrible code. I'm not sure how obvious it is, but it's full of units, discarded results, and even a callback. It's as if descriptive types and streaming is not a thing anymore, or wasn't in the past at least. But the structure pretty much matches the diagram we saw earlier. So we have a list of batches here, and we start by going over all the batches and giving them a security rating and ranking them. And then the optimizer is adding pre and post tasks that are the thing that's supposed to tell us when to open and close the sandbox. Then we open the sandbox and do the security trace and submit it to the job queue via callback. And seems like we should be kind of safe in opening and closing the sandbox, because we're doing acquire and release of our provider. But this is misleading, because the sandbox optimizer actually splits up the opening and closing procedures into different executions. So we might open the sandbox in one batch, but we're supposed to close it in another. And so why did we forget to close the sandbox? So in the logs, we saw that the relevant behavior here are empty list and empty options. So empty list doesn't seem to be part of the problem, because it happens within the acquire release block. So that shouldn't be a problem. But where did the option go? So it might be kind of easy to miss, but we have an option here hiding within a very polymorphic function. And it's a general kind of thing that very polymorphic functions mixed up with units tend to be kind of confusing and hiding things. So it doesn't make it obvious that something different is happening here. But what we're saying here is that we will only perform the side effect for this batch if the option is non-empty. So if the side effect for the batch was to close the security sandbox, we won't be doing that, and so we'll forget to perform the cleanup that we're supposed to do it. And now seeing how kind of convoluted this code is, and we have many lists and many for eaches and stuff like this, it's easy to miss, and it's a kind of a small change to make that might not be obvious. So we can see what happens in our problematic scenario. So what we see here that we start with the first batch. The optimizer sees that we have two occurrences of P3. So it says to open the sandbox on the first one and close it on the second. But on the second, we have an empty option. So when we get none for the second provider, we skip the closing. And then in the following input, we get another batch from the provider P3. And so we are supposed to open the sandbox, and that's where we fail. So the question is, how do we fix this? I'm sorry it's so quick, but I really don't have any more time. So we might wonder, how do we fix this? So we might ask ourselves, why is there an option there to begin with? And apparently it's some weird integration with legacy code. So we have this rank legacy call that is something old, blocking and side effecting and erroring, and so we wrap it in a try, and then we swallow the exception with the option. Now, swallowing exceptions without a trace is never a good idea. So we might as well integrate the exception into our effect and avoid the option altogether. So now we have a new signature. Instead of unexceptional IO, we have a task. The task can fail, so it's no longer a non-failing effect. And but now the ranked batch now doesn't have any options. So we don't have an option that can fail our closing procedure. And with this in place, we can rerun a property. And it's actual success. That's the real green thing. And the non-corruption property we just defined is actually holding for, seems to be holding for our code, or at least for the mocked version. So there are still issues left. So as I said, we verified only the mocked version, and we did it randomly, so maybe we're still missing something, but we never verified our real system, so because we didn't manage to reproduce the bug there. We also have no idea why the none occurred in the first place, so that's another mystery. And we have no idea why it happened on the upgrade between Java 6 and 7, because again, we don't know how the none came to be, so who knows. So we can kind of look at the code, the rank legacy function, and try to guess. So there's this assigned security rating thing, which is as a mere security thing. We probably don't want to touch the data science kind of things, but seems like a plausible candidate for failure. But we have no idea. But so we might, but at least we no longer swallow exceptions. So we might get some insight if the exception is thrown again in production, and we'll get some real logs and might debug it further. But the sandbox at least should be safe for now. Okay, so we deploy our fix to production, and we hope for the best. That's usually how it goes. And success. No more security sandboxes corrupt exceptions, which is great. But we're now starting getting occasional illegal argument exceptions instead that weren't there before. And it says comparison method violates the general contract with an exclamation mark, no less. No idea what that is. And since when Java is so excited about exceptions, I don't know. But at least now we have an exception, so we can see where it throws. And it's throwing on this line, on the sorted. So who would have thought that sorting would be exception throwing, and since when sorting is throwing exceptions and why. But now we can go back to our old hammer of print line debugging as usual. So that's the input it throws on. It's long, I think. So there's not much we can learn from it. It looks kind of random. But we have property-based testing. We can shrink this to something more comprehensible. Now that we know where it's going, we can write a new property. So this property is a very basic requirement. We say that for all inputs of our lists of ranking jobs, we shouldn't throw exceptions. Seems reasonable. So it's a bit tricky to get this property to actually fail. It requires some configuration, but we finally can get it. Here's the failure. And I have no idea what happened to our shrinking. So it tried to shrink, obviously. It has 700 shrinks, even more, but still kind of huge. Suspiciously, all the lists it lists fails on, it always somehow of length 32. So probably not a coincidence, but who knows. But we no longer have to debug strange properties and generators. We actually have a stack trace, so we can just take a look at the actual code. So we can dig into the problem. So here's some Java code. So here where it throws the illegal argument exception. So I'm not as fluent in Java as I used to be, but that's some seriously impenetrable code. I have no idea what a gallop, whatever it is. So there's a min gallop, and I don't know. And it goes on like this, like for quite a bit. So no way I'll figure it out. Because I won't figure it out by staring at it. Probably most people are not really into looking at code like this. So the stack trace wasn't that helpful. But it is the JDK, and unpleasant as it may be, we can just read the documentation, sadly. So apparently sort is allowed to throw when the comparable that was passed to it violates its contract. So it might be an interesting discussion whether throwing in sort is the right thing to do, but we can just move on to the documentation of comparator. So here's the contract that we're supposedly violating. So surprising to see it in Java, speaking of contracts and properties, but we have a property that the compare function must obey. In this case, something to do with flipping the arguments and sign inversion. Java is literally telling us which property we need to test. And there are a couple more. So it looks like something that you might straight out of Scala Z or Cats or whatever. And these libraries actually have these properties defined, and we could use them to check our properties, but we can write it ourselves. Translating the documentation into code is fairly straightforward. So here's the first property. So it's just a translation of the documentation directly into an executable code. And with a bit of trickery, we can spell out the other properties as well. And we can run those. And it fails immediately and very quickly on the first property. So apparently we're violating the flipping the arguments and flipping the sign thing. And we got a very, very minimal reproduction. So if we run this test multiple times, we see it's always a couple of fold proteins jobs, and it's always, that always have the same security rating. So we can finally now pinpoint our bug. So that's the ordering that we're using for rank job. We even have a comment explaining what it should be doing. So we order by security rating, but as a tiebreaker, we prefer protein folding. We really do want to give back to the world. It's in our DNA, so they say. It's also a business requirement, so we have to do it. So we start by ordering by security rating, and if that's equal, we look at the job type, and if the first one is protein folding, then that wins. If the second one is folding proteins, that wins as well. And can you see the bug? So if both jobs are fold proteins, then we get 1. But if you flip the arguments, you still get 1 because the first job is still fold proteins. And so we broke sign inversion, which required the result to be -1. And the fix is actually very, very easy. So if both arguments are fold proteins, it's just 0. So flipping the sign of 0 is still 0, unless you're using doubles, and then, I don't know. So we can run our properties again. And finally, this fully resolves the original bug, so no more exceptions on sorting, and all the properties are in place. And we can now recap our full bug. So it's been a long way, but we started out with a buggy ordering instance that sometimes, but only sometimes, triggers an exception in sort, but only on relatively long lists, at least 32 in length, which is quite rare to generate and rare to get. It's because the Java sorting algorithm works in chunks of 32. So that explains why the minimal examples were always that number. So the exception throwing behavior is something new that was introduced, I mean, like a decade ago or so, something new that was introduced in Java 7. So this explains why the bug happened only after upgrading. And so we had some poor integration with legacy code that swallowed exceptions that were, so instead of proper exception handling, we just swallowed it silently, never a good idea. This all was hidden in very imperative code that was additionally very poorly typed, unit being a very particular culprit here. And with more layers of obfuscation due to weird batching, because streaming is not a thing that we can use apparently. It's as if someone kind of tried to obfuscate the code on purpose. Obviously not me and not for this presentation. And then we applied a rather naive way to optimize our resources, which got lost in all the badly written code. And the result was this long-winded bug we finally figured out. So with the aid of property-based testing, which was the whole point, but it's no wonder it was so difficult to nail down, because the circumstances for the bug are quite specific. It has to be a very long input in many layers, and you have to generate it properly, and so it is quite an effort. Nonetheless, we managed it. So we can conclude now. So we used property-based testing as a very powerful, I think, debugging tool. All the pillars of property-based testing were present here. So we had some simple properties defined for our system. We used randomization to explore the state space and reproduce the bug. Shrinking helped us minimize the bug into something we can actually debug and comprehend properly. And figuring out the mechanics of what actually went wrong. And I hope this study illustrates, case study illustrates that the point that this tool is powerful enough to be used for real production systems, not just toy examples and mathy stuff. Nothing is magical though. We did need some fine tuning and had to kind of use finesse to generate the data properly, which is something that requires practice. But this should serve to show that property-based testing is more than math and reverse. You can do stuff that's relevant to your maybe day-to-day work as software developers. And as a final twist, it appears that sometimes even Java can throw math at you. So we got to use properties in the more classical setting as well. And this concludes this study. And one last thing though, as we deployed the fix, the data science team analyzed some data, as they usually tend to do, and came to a surprising conclusion that strangely the broken sorting was more profitable for our company than the correct one. So luckily Java got our back, so we have a flag we can enable that reverts us back to the other. So we could have just avoided the whole thing in the first place. Thank you.